All right, gang, here we go. So this is Physics, Unit 2, Part 4. All right, so we're starting Chapter 4. We just wrapped up Chapter 3. Chapter 3 was Parts 1, 2, and 3 in Unit 2. And then Chapter 4, it starts on Part 4 here. All right, so this is Newton's first law, all right, in this video. Okay, so here we go. All right. So, what is a force? Now, be careful. Now, this is not what is the force, right? It's not. It's not a Star Wars thing. It's what is a force. Okay. And so, in class, we kind of walked through these questions, kind of developed our own definition of a force. All right. And then, so this is really the definition of force. All right. Forces are anything that changes motion. Okay. So, if you act on something and it changes its motion, okay, then that is defined as a force. All right, it could be a push or a pull or just a field that's pushing and moving it. Okay, so it stops movement or changes the direction of movement. So you've got to think about it, and this is an important part that kind of throws people off. Okay, anytime that you're changing the direction of the movement, you're changing that vector, right? Because a vector is has two parts, right? It has magnitude, all right, magnitude and direction. Okay, so anytime you're changing the magnitude or changing the direction, you're changing what that vector is. So if it's got some sort of velocity, if it's headed this way, and if you don't, even if you don't speed it up or slow it down, if you turn it, then it's actually moving. Okay, and so its direction is changed, and so therefore it had some force that acted upon it. Okay, so it can cause an object to speed up or slow down. So in this case, there's this picture here of this girl throwing this ball. Okay, and it looks like a softball, maybe it's a baseball, and it's just a little bit closer. Who knows? Okay, so she throws it, and so when the ball was at rest in her hand, she picked it up. It was moving, and then she launched it, and so now it was moving through the air. Okay, and right now there's no forces acting on it. Okay, because it's in the air. Well, gravity is a force and it's acting on it, but horizontally there's no force, making it move towards us. Okay, here the person catches it. That ball comes in here this way, and it got acted on by a force, and that force was the glove stopping the movement of the ball. It slowed it down very, very quickly, so the ball stopped moving. Here, this guy hits the ball with the bat. Okay, and so when it hits the ball, the ball's coming in at the bat, and then the bat swings and hits the ball, and so the ball was headed this way, and then all of a sudden it's going to start heading back out towards the pitcher in the field. All right, because there was that change in movement, change in direction, and possibly even an increase in velocity. All right. So forces come in two different flavors, if you will. First of all is contact forces. All right, so these are things that actually require physical interaction between them. Okay. So it's anytime you have a push or a pull that's directly acting between these things. So the perfect example is the baseball with the bat. This is a contact force. The ball comes in, the bat makes contact, and the ball reacts and moves somewhere else. All right. The other flavor of forces is a little bit more fun, and we won't really mess with these until second semester. And these are field forces. Okay, and so these are things that actually create force fields. Yes, you heard me. Force fields is a thing. Okay, force fields is a thing, and so these are things that create a field of forces that act on your object. So, like if you've ever taken a balloon and rubbed it on your hair. Okay, and then you can tell, and then you hold up something like a piece of paper or something, and you can see that paper start to bend towards it. That is a field force. Okay, because it's making that paper move without actually touching it. All right, so great examples of these are gravity. Gravity is a field force, right? You could be standing in the air, right? And the gravity is still pulling on you, even though nothing's specifically touching you. That's why we can have gravity in a vacuum. Right, a lot of people think vacuums mean there's no gravity. That's not true, because gravity, occurs regardless. A lot of the people equivalent gravity or vacuums with being in space, and in space things float there because there's less gravity or microgravity. Okay, but really you can have a vacuum on Earth, right? We can create one in a classroom with our vacuum pump. Okay, so anyway, so those are field forces. All right, let's see. All right, unit of force. So these are important. Okay. So the SI unit of force, and this is like the only one people use really, is the Newton. Okay, and the Newton is a combination of other SI units. Okay, so the Newton is equal to 1 kilogram per meter times meter per second squared. So so it's the force. So a 1 Newton is described as the force required to accelerate a 1 kilogram mass at a rate of 1 meter per second squared. So that's why it's a kilogram times meter per second squared, because it's the force required to accelerate 1 kilogram at 1 meter per second squared. Remember, this is 1 meter per second squared. This is, this is acceleration. Okay, acceleration. All right. Other ones are here. We got the CGs here, and I can never say this word right, but the avoirdupois, or whatever. But it's the slug. All right. So anyway, so it's kind of fun, but really, like, you can kind of ignore these. This is the big one here, the SI unit. Okay. Anyway, kilograms, etc., etc. Cool. All right, now force diagrams. Now this is exciting stuff here. Okay, forces are vectors. I know you really thought we were done with vectors, but not true. Vectors are going to be here from now until May, when you are done with physics, at least until you get to college. Okay, so forces are vectors, meaning they need these two things. They need magnitude and direction. Okay, so you got to come up with a magnitude and you got a direction. Remember, magnitude is defined as the length. Okay, the length. And then direction is where you're pointing. Okay. All right, where are you pointing? So a force diagram is something specifically that shows us all the forces that are acting during a given interaction. Okay, so a force diagram is when you have an interaction. So here A is a force diagram. You've got a car hitting a wall, and in class we're going to we demonstrated this. We've got a car, we're going to launch it at a textbook showing, and we're going to draw out these force diagrams. So you can see that, well, these up and down ones, these are always present, because if you think about it, gravity is always pulling down on whatever it is. So this car is being pulled down by gravity. So that force diagram is here. Now notice from the center point right here, it's pulling down, and equal in magnitude but opposite in direction is this other arrow pushing up. Where do you think that arrow comes from? Well, it has to come from the ground that's pushing up on our car. And if the ground has to be pushing as equally hard up on our car as gravity is pulling down. If the ground stopped pushing as hard as gravity is pulling down, then our car would fall into a sinkhole. Or if for some magical reason ground started pushing harder than gravity's pulling down, our car would start to, the ground would start to rise and our car would start to fly. Kind of nuts. But anyway, so these up and down arrows are always here. Notice that even the wall has them, right? From the magnitude. Notice this arrowhead is a little bigger. That doesn't mean anything. We don't care how big your arrowhead is. We care about the distance from your vector. So from the center point, these are equal in magnitude. Your wall is getting pulled down towards the ground, and your wall is pushing back up on the earth, or the ground is pushing back up on the earth against the wall, equal in magnitude. All right. So that's nice and handy, but then the force diagram shows us during an interaction. Okay, so this car ran into this wall here. So when this car ran into the wall, it pushed against the wall this way, and then the wall pushed back against the car. All right, so we get this interaction and these forces that are acting against each other. Notice how they're equal in size but opposite in direction. Okay, that's important. All right. Now, a free body diagram is a special kind of force diagram where we only talk about the forces that are acting on the thing that we care about. All right. So specifically with this car that's running into the wall is going to remain unfazed, right? Unless this guy's going really, really fast, or he's got like a really super dense bumper. Like this brick wall is really not going to go anywhere. All right. So that's not the object of interest. It's not really interesting because nothing's really going to happen there. So what we really care about is the car. So what we draw is what's called a free body diagram, and it's called a free body because we just essentially like pick the car up and we put it out in free space where we can kind of just draw arrows on it. Okay, so that's what I think about it when I hear free body diagram. So we take the car and we draw these force arrows, these force vectors showing us all the same things. All right, so that's our free body diagram. So let's talk about each of these forces again real quick, just so we understand what's going on. So this force that's pulling down, we'll call this F1, this or Fg, because it's the force of gravity. Okay, and so gravity force pulls down. So is this this would have to be, is this a field force or a contact force? Well, we already described that gravity is a field force, so we're going to go ahead and define it as a field force. All right. Now this guy here, this guy is the force that's pulling up. Now this is defined as the normal force. All right, or Fn. Okay, the normal force. All right, I'm going to put that in parentheses so you can write it down. So that's the normal force. All right. So normal force is defined as the vector that points directly opposite of gravity. All right. That's the normal force. It's the force that counteracts gravity. This is coming from the ground pushing up against us. Now think about it. Is it a field force or is it a contact force? All right. Well, it's caused by the contact on the ground. And the ground isn't causing a field that's pushing up on the gravity. It's just pushing up against gravity with contact. So this would have to be a contact force. All right. And then finally, we've got a force vector, this. So this is the vector representing the force that the wall is putting on the front of the car, and it's pushing it to the left. All right, so as it's pushing it to the left, our car gets pushed to the left by the wall, etc., etc. So this would have to be a contact force. All right, contact. And this guy doesn't really have a special name. This is just a normal force, so you'd name it like F1, F2, something like that. All right. So imagine this. So you're pushing a puck across. You've got an air hockey table, and you push a puck across it, versus pushing a book across a lab table. All right. Now think about what happens as you move each. So which of these three does it take in each case? So if you're pushing a puck across the table, so we'll label the right answer. Situation A versus situation B. All right, so when you're pushing a puck across an air hockey table, which describes what we need to do to maintain a constant speed? All right, so with the air hockey table, this is virtually friction free. It doesn't really, there's no resistance. Once you get it started, it's going to keep going in that direction. So really, if we just give it a quick push and then release it, then it'll just keep going at a constant speed, right? So this would be what we need to do for A. Now, if we're pushing it across our lab tables, well, we've got our books. If we just give it a quick push, we'll push it, and then it'll slow back down again, right? It's not a constant speed, it's slowed back down. So now we need to keep adding push, right? So it's either this one, and so the first one's right out for situation B. Maintain a constant force as you push the object. That sounds about right. What's the third one say? Increase or decrease the force as you push the object. So if we increase the force on our push, then the book will start moving faster and faster, then depending on how hard we push it. So obviously, B, this one has to be it if we want to keep it moving at a constant speed. All right. So Newton's first law here, this is very important. This is kind of where we've been headed all the way here, from chapter 4 in this whole unit so far. All right. So Galileo came up with this idea that objects maintain their state of motion. Okay, so he kind of came up with this idea, and he did it through experimentation. Newton came along and said, hey, that's a pretty good idea, but let's make it better. And he came up with this guy here. This is Newton's first law. And you've probably heard it before. An object at rest remains at rest, and an object in motion continues in motion with constant velocity, okay, unless the object experiences a net external force. So your objects are going to keep going the way they're going until some new force acts on it. That's essentially what it says. All right. So you need to have this memorized, or at least be able to, describe the basic principles of it. Okay. So this is also called the law of inertia. Now, inertia is defined thusly: it's the tendency of an object not to accelerate. All right. Mass is a measure of inertia. So the more inertia something has, the less easy it is to move it, right? Because if you want to move something, that means you want to accelerate it, right? Because any acceleration is defined as a change in velocity, and velocity is a vector. So if we want to change the velocity, that means we're trying to change the vector and change either the motion or the direction of it, the motion or the magnitude or direction of that velocity vector, right? So if our thing has a lot of inertia, that really is just how much mass it has. Okay, so that's really how hard it is to move. So the more mass this thing has, the harder it is to start moving it. So therefore it resists change in velocity and therefore has more inertia. All right, so let's look at some examples here. All right, so which one of these two has more inertia, a baseball or a tennis ball? Well, remember we can use, I just dropped my pad. So remember we can use the idea of mass to identify inertia. Okay, so which one has more inertia, a baseball or a tennis ball? Where a baseball is more massive, so therefore it has to have more inertia, so it's got to be the baseball. All right. Now here's another interesting one. So we've got a tennis ball moving at 125 miles per hour. That's pretty fast. It's pretty good. It's a good whack, right? Or a baseball at rest. Well, which one do you think is going to have more inertia? Well, it's still the baseball because the velocity is not a measure of the inertia. Remember, a measure of inertia is the mass, and the baseball still weighs more, so therefore it still resists that movement and more than the tennis ball does. Okay. Now before, remember, over here we talked about the specific idea of on Newton's law, we specifically talked about this idea experiencing a net external force. So now let's kind of hit on this idea of a net force and what exactly that means. All right, the net force is the sum of all the forces that are acting on it. Okay, that's the net force. So it's kind of like calculating your gross versus your net pay. That's the idea of the net. We're talking about, well, what's the total result of all the forces that are acting on it once we take into account everything that's involved. All right. So with our original car, well, this isn't the car running into the building. This is a different car, even though it looks exactly the same. All right. We've got all these forces that are acting on it, and this car is moving at a constant velocity. Okay, so we've been told that it's moving down maybe a highway at like 60 miles an hour, and it's just going along. Now gravity's pulling down on this car, but the ground is pushing up on the car just as hard. So that's good because that's keeping us on the ground. Remember, again, if gravity is pulling down harder than the ground is pushing up, then that means we're going to be in a sinkhole. We're going to be pulled down into a pothole or something like that, or vice versa. We might start flying. Well, that would be fun too. All right. Now, our forward and backward, now this is where things are interesting. Since we're moving at a constant velocity, that means our forward velocity has to be equal to the resistance of the tires on the road, okay? Or, so there would be friction of the tires on the road, but then there's also air resistance that are hitting the front of the car. So we've kind of got both going on here, all right? So, but because we're moving at a constant velocity, that means all of these forces have to equal 0. So this is an important idea here. Velocity is constant because the net force is 0. So if you ever run into a case where your velocity is constant, then you're looking for your your net force being equal to 0. All right. So if our net force equals 0, then we're in a state called equilibrium and all our forces are balanced, okay? So this car we just looked at was specifically because our net force was equal to 0, then we are at equilibrium. Now, let's just pull back here for a second and let's think if our forward momentum, if we hit the accelerator and the force going forward was greater, well, that makes our car accelerate, right? So that's made it so our net force is no longer 0 and it's pushed our car forward. Vice versa, what if we hit the brakes and we apply friction to the rotors and the brakes, and so our tire spins slow down, so therefore there's less forward momentum but just as much resistance, so therefore we're going to slow down our net force is going to be pulling us backwards. All right, and then so we get this idea of this fishing line here. Okay, so we've got this fish and it's getting pulled up. The fish, if you've ever been fishing, you know the fish don't really like to get pulled out of the water very much. Okay, and so we've got this fish that's sitting here. Okay, and we're pulling up on it with the fishing line, and right now, because the fish is not moving, notice that our acceleration is equal to 0, meaning that our velocity is not changing. Okay, and so the fish is stuck there, and then they're going to stay there just like that until either the string breaks, right, and then there's no force pulling them together, and then they'll go their separate ways, or they'll change when the person pulling on the line decides to start pulling harder, or the fish gets tired and stops pulling, and then they'll get pulled up out of the water. All right, so when we're at equilibrium, there's really two options. Okay, in the case of the car, we were at equilibrium and we were traveling at constant velocity. right? But when we are here in this fish, we're at a net force of 0. Our acceleration is equal to 0, and so we're at rest. So these are the two cases. When we're at rest or traveling with constant velocity, our net force is 0. All right, so that's a very, very important thing to know. All right, important. All right. All right. So we already talked about that. All right, let's do a practice problem, and then we'll call it good. All right, so we got an agriculture student, and he's designing this. He's designing a support system to keep a tree upright. So he's already attached 2 wires to the tree, and he's put them at right angles to each other. All right, and they're parallel to the ground. All right, one wire exerts a force of 30 newtons and the other exerts a force of 40 newtons. And we want to determine where to place a third wire and how much force it should exert so the net force on the tree is 0. All right, so we've got a tree, so we'll draw a tree, okay, just for funsies here. And then it says that we've got 2 forces and they're being pulled parallel to the ground. So maybe he's got them attached to stakes or something next to the tree. And so we need to figure out where our third wire needs to go. All right, so this is the middle of the tree. So we're looking down at the tree, right? So we're up above the tree looking at these wires. All right, so we've got these 2 forces. One is going up here, and it's 40 newtons. All right, and then it said is there 40 to 30 newton, and they're at right angles to each other. So, and then here's our 30 newton. Okay. All right, 30 newton force going that way. Now remember, forces are vectors. So if we want to figure out what we need to do in order to perfectly counteract that, because if you want to support a tree, you don't want to pull it one way or the other. You want to pull it so everything's pulling exactly equal. And if we're pulling it exactly equal, it'll keep the tree straight, right? So we need to come up with some third force that's going to come out this way somewhere, right, in order to counteract these 2 forces. Now let's think here for a second. So we need to come up with this force here. All right, so what we can do is if we add these forces together, if we put the 40 here and the 30 here, oops, yeah, whatever, that's close enough, the 30 here, okay, we end up, and we could find this value of the resultant, right? We could find this resultant. Now if we were going to look at it here, if we move this guy parallel up this direction, right, our resultant would be this line right here. Okay, this would be our resultant. And so the resultant would be the result of those 2 forces that are already pulling on it. So really what we need to do is find the opposite of the resultant. So by opposite, we mean equal in magnitude but opposite in direction. Okay, so if we can find the magnitude of that resultant and the angle of that resultant, or this angle here, okay, then that means we can find exactly what's going on. So maybe we'll erase this triangle and we'll redraw it so it kind of matches our original diagram a little better. Let's see, where's my eraser? So let's erase this guy and we'll redraw it here. Pointer options pen. All right, so let's redraw our triangle so it kind of matches what we've drawn in our diagram. All right, so there's our resultant. Okay, there's our 40 here. There's our 30 here. All right. So we need to come up with the value. So we're going to, now it's just simple vector math now that we've solved it up. So we've got to find this value. So C is going to be equal to the square root of 30 squared plus 40 squared. Well, 30 squared is 90, 40 squared is 160, so that's 250. All right. So that would be, or 2,500, sorry. And then, so that would be, so C is equal to 50 newtons. All right, so that means, so our hypotenuse is equal to 50. But remember, it's a vector, right? Forces are vectors, so we need a magnitude and a direction. So that's the magnitude part. So we also need to find the direction. Well, the direction is going to be the value of that angle, right? That's going to tell us where we need to go. All right. So we can use that. So we'll just find tangent. Use tangent. So remember, tangent of theta is equal to opposite over adjacent. Opposite over adjacent. So that means theta is equal to the inverse tangent of opposite over adjacent. Okay. So our opposite value is equal as 30. Okay. Oops. Yeah, our opposite is 30. And our adjacent is 40, all right? If we plug those guys into our calculator here, we'll say inverse tangent of 30 divided by 40, and I got 36.87. All right, 36.87 degrees. Now, so let's think about where that angle is. That angle is right here, okay? But we want the exact opposite of that. So that's 36.87, okay? But this guy here, this is going to be our opposite vector. So remember, so this guy here, our opposite vector has a vector magnitude of 50, but we need the direction. All right, so we got to figure out, well, how exactly are we going to define where the new vector is? All right, well, we know that that vector here, okay, these two vectors from there to there are 180 degrees apart. Okay, maybe it'd be better to draw it on this. So this to there is 180 degrees apart, right? But we know from here to here, our vectors, from here to there, our vectors are 36.87 degrees apart. So if we take 180 minus 36.87 degrees, all right, we'll end up with this angle here from the 40 down to the 50. All right. All right, so we'll take 180 minus our answer. We get 143 degrees. All right, 143 degrees. And so, and that would be east of our, 143 degrees from, so just thinking about the west way, from the 40 Newton wire. Okay. All right, so the third wire we need to place needs to be at 143 degrees from the 40 Newton, and it needs to pull with 50 newtons downwards. All right, so that's how you would go about solving this kind of problem. All right, make sure you do lots of practice problems in the part one part of the packet. All right, remember, the practice problems are the #1 way to prepare for quizzes and for the exam that's coming up. All right, let me know. Come see me before or after school if you have questions.